In this video, we're going to talk about what a hyperbolic trig function is. The definition of a hyperbolic trig function is not based on trigonometry at all. It's actually based on a hyperbola, hence the name. We'll see in a minute what the picture looks like and how it relates to trigonometry and how it got the name hyperbolic trig, even though it's not trigonometry based. In fact, hyperbolic functions are based on the graphs of e to the x and e to the minus x, which are of course two exponential functions. At the top of the screen, you can see the two definitions for the hyperbolic sine of x and the hyperbolic cosine of x. Now, we pronounce these sinh of x and cosh of x. Sinh of x is e to the x minus e to the minus x, all divided by 2. And cosh of x is e to the x plus e to the minus x, all divided by 2. In that sense, the sinh of x and the cosh of x are conjugates of one another. And as you might expect, this will affect their Pythagorean identities. If you look at the two graphs at the bottom of the screen, the dots that are red and dashed, these lines are the graphs of e to the x divided by 2, the front part of each of the definitions, and the graph of e to the negative x divided by 2, the back part of each of these definitions. Finding the graph of cosh is somewhat simpler to understand than the graph of sinh, so let's take a look at it. When you're looking at the graph of cosh, you're going to take the graph of e to the x, take the y value at a particular point, and add that y value to the y value on the graph of e to the negative x divided by 2. That will give you the point on cosh of x, which is e to the x plus e to the minus x, all divided by 2. So the graph of cosh of x is the one you see here in blue. That means that cosh of x is symmetric with respect to the y-axis, which means that it is an even function. So the cosh of negative x must be just the cosh of x. It is y-axis symmetric. If you change the sign of the x, it will not affect the value of cosh. When you look at the graph of sinh on the left, the definition for sinh is e to the x divided by 2 minus e to the minus x divided by 2. So come to the graph in the red dashed line for e to the x divided by 2 will come out to 1. It looks like that value is somewhere around 1.5. Then I find the value on the graph of e to the minus x divided by 2, which looks to be less than a half, so maybe 0.4. So the value on sinh should be this 1.5 minus a negative 0.4, which gives us something relatively close up here, right? So in order to compute them, you have to find the value on each of the graphs and then do the subtraction. You'll notice when looking at the graph of sinh that sinh is actually an odd function. It is not symmetric with respect to y. It is not symmetric with respect to x. But if you were to fold this piece down in from quadrant 1 into quadrant 4, and then fold it over into quadrant 3, it would lay on top of itself. This makes sinh an odd function. As a result, if you replace the x with negative x, then the sinh of negative x becomes negative the sinh of x. Hyperbolic trig functions come up in all kinds of applications. One of the most well-known application of a hyperbolic function is what's called a catenary, C-A-T-E-N-A-R-Y. A catenary function is basically any material that is suspended under its own weight and is only being dragged down by gravity. So if you look at the bottom picture, we have a chain here which is being suspended between two posts. Even though this graph looks parabolic, in fact it is not. It is described by a catenary function, which is usually based on cosh. The curvature of the catenary is not as rapid near this lowest point as it would be on a parabola. It's the change in the curvature that determines that it is in fact a catenary and not a parabola. Power lines are another example of catenary functions. All power lines are suspended between their two posts, and therefore they are catenary functions. Many of the arches that you see, whether they're in sports domes or the St. Louis Arch or the arches on the Golden Gate Bridge, are also catenary functions. These are not the only applications in which you see hyperbolic functions. If you have light or electricity or magnetism that is sort of dying out or extinguishing or fading away, that pattern can also be described with a hyperbolic function. They're not called catenaries because it's not suspended under its own weight, but it is described by a hyperbolic function. We will call them both hyperbolic functions and hyperbolic trig functions, despite the fact that they are not actually based on trigonometry. Let's take a look at the unit circle and the hyperbola on which the hyperbolics are based to understand what the relationship is and why they're called hyperbolic trig functions. In the center, you see a graph here of the unit hyperbola. By unit hyperbola, we mean that from the center of the hyperbola, which is at the origin, you move right one and left one. Those are the vertices on this hyperbola. To find the asymptotic lines, again, you have to do the ghost vertices, which would also be up one and down one, and draw the diagonals of the box. Now, you can see that there is a red-shaped area over here. This area right here corresponds to half the measure of this angle right here, which is formed by connecting the origin, the center of the hyperbola, with a point on the right arm of the hyperbola. If we measure this angle here in radians and call it A, then the area that is carved out between the angle from the center of the hyperbola to the point on the right arm, following the hyperbola down to the x-axis and back again to the center, that area is exactly the measure of the angle in radians divided by 2. We can again call the coordinates of the point where it hits the hyperbola as the cosh of the angle and the sinh of the angle, similar to what we do with the unit circle. Let's put the unit circle up side by side with the hyperbola and see what their relationship is. Here on the left, you see the normal unit circle on which our trigonometric system is based. If we measure the angle here, centered at the origin, with theta, the formula for the area of the sector carved out by that angle is given by pi r squared times the angle divided by 2 pi. This gives us the formula of 1/2 r squared theta. If we're on the unit circle, r squared is just 1, so that the area carved out by the sector on the unit circle is in fact the angle divided by 2. This is the same relationship we saw on the hyperbola when the angle here, also called theta in radians, carves out this odd shape next to the hyperbola in quadrant 1. This is one of the reasons why the hyperbolic trig functions are called hyperbolic trig functions instead of just hyperbolic functions, though you'll hear them called that as well. Let's take a look at some more of these graphs. Here in this picture, we see the graphs of sinh of x and cosec of x side by side. These have the same relationship that we see in the regular trig functions, in that the reciprocal of sinh is cosec. So 1 over sinh is cosec, which is basically just the reciprocal. Turn the exponential function upside down. When you look at the graph, you can see that where sinh is 0, cosec has a vertical asymptote. since the reciprocal of 0 is undefined. Where the sinh of x goes to infinity, the cosec of x must approach 0 from above. Where sinh goes to negative infinity, cosec has to approach 0 from below. That's the relationship between these graphs. We'll see the same thing for cosine and sec. In this picture, we can see cosh of x and its reciprocal function, hyperbolic secant. We pronounce the hyperbolic secant sec. So when you look at these, they are just straight reciprocals. If you're looking at the graph of cosh, when you take the reciprocal of 1, it is still 1. So the graph of sec is still hitting this point at 0, 1. As cosh goes to positive infinity as x goes to infinity, its reciprocal must approach 0 from above. Again, cosh approaches positive infinity as x goes to negative infinity, so sec must approach 0 as x goes to negative infinity. That gives the relationship between these two reciprocal functions. We see the same thing with tang, hyperbolic tangent, and cotang, hyperbolic cotangent. In this picture, we can see both the hyperbolic tangent function here in this aqua blue and the hyperbolic cotangent function here in yellow divided into two pieces. Again, when the hyperbolic tangent function is 0, its reciprocal function, hyperbolic cotangent, will have a vertical asymptote. Now, when you're looking at these, you will notice that hyperbolic tangent, pronounced tang, is also sinh divided by cosh, just as we have tangent being the sine divided by cosine. This is one of the reasons that the hyperbolic trig functions got the trig added to their name. Now let's take a look at some of the identities. On this page, we see the various hyperbolic trig identities on the left and the basic 6 hyperbolic trig derivatives on the right. Notice that the basic Pythagorean identity is not what we normally have for regular trig functions, cosine squared plus sine squared equals 1. We get that because regular trig is based on the unit circle, and the formula for the unit circle is x squared plus y squared equals 1. Hyperbolic functions are based on a hyperbola, which have the subtraction in the middle. So the hyperbolic trig identity is cosh squared of x minus sinh squared of x equals 1. They're just close enough to make it a little bit confusing, which is why I allow you to put the formulas on a formula sheet. You can also find here some of the double angle formulas and the other two hyperbolic Pythagorean identities down here at the bottom. Notice that these are not exactly what you get with the trig identities. They're different because hyperbolic trig functions are based on hyperbolas and not on a unit circle. However, when you look at the derivatives, again, we see a lot of similarity with what we have with regular trig functions. The derivative of sine is cosine, and the derivative of sinh is cosh. However, unlike with cosine, where the derivative is negative sine, the derivative of cosh is positive sinh. This can be confusing, so be very careful. When you're looking at the derivative of tang, it is sec squared. The derivative of cotang is negative cosec squared. This seems to match what we have in the normal trigonometry. But the derivative of sec is not positive sectang, but negative sectang. The derivative of cosec is negative cosec cotang. The two that don't match what we expect are the sec and the cosh derivatives. We can also write these in terms of the basic integrals, and you'll see those basic integrals written here. You can find a sheet on D2L that will help you to print these out in an easier form. Just as we have inverse trig functions, we also have inverse hyperbolic trig functions. In this case, they are again giving you the angle that gives you that particular location. So again, the inverse hyperbolic trigs are also giving you this value, but in this case, it corresponds more to that area as opposed to the angle in radians. Now, these are the graphs of the inverse hyperbolic trig functions, but we won't be doing a great deal of work with them. You will notice that they have chopped off half of the cosh function so that its inverse function would also be a function. Otherwise, if you inverted both arms of cosh, you would still have a curve, but it would no longer pass the vertical line test, so it would not be a function. Let's look at the others as well. Here on the left, we see the inverse hyperbolic tangent function, and on the right, the inverse hyperbolic cotangent function. On the next part, we can see the inverse hyperbolic cosecant function, and on the right, we have some of the relationships for these inverse functions. It is true that the reciprocal of the inverse secant hyperbolic function is the inverse hyperbolic cosine of the reciprocal function 1 over x. Sometimes these are good to know. You may want to write these down somewhere as well. These formulas represent the derivatives of the inverse hyperbolic trig functions. These are certainly something I would not expect you to have memorized. You'll notice that they are again quite similar to what you would see for the inverse trig functions, but again it is the inverse hyperbolic cosine function and inverse hyperbolic secant function that are somewhat unusual. Now, what we will be doing with the hyperbolic functions is simply computing some arc lengths, some volumes of revolution, and perhaps a surface area using these functions. We are not going to do anything other than what we have already learned in this course. You're simply going to use one of the hyperbolic functions to perform that action on. This is the end of the video on hyperbolic functions.